Okay, now let's see how we can design or select heat exchanger according to these two different methods, LMTD, which we learn up to now. Okay, here we have a double pipe heat exchanger, as you can see here, and we are going to know what information we have for this heat exchanger and what we are going to find. A double pipe parallel flow, as you can see, it is parallel flow. A double pipe parallel flow heat exchanger is to heat water. So the cold fluid actually is the water. It is going to be heated. Its specific heat is 4180 joule per kilogram degree Celsius, and its temperature, initial temperature is 25 degrees Celsius, is going to be to increase to 60 degrees Celsius, and also its mass flow rate is 0.2 kg per second. The heating is to be accomplished by geothermal water. So the hot water is geothermal water, which its specific is it is different from the cold water. It is 4,310 joule per kilogram degree Celsius, and its initial temperature is 140 degrees Celsius, and its mass flow rate is 0.3 kilogram per second. As you can see here, this is the hot water in the inner tube, which its initial temperature is 140 degrees Celsius, and the cold water in the shell side, or second tube actually, second pipe, is the water, cold water. The inner tube is thin walled and has a diameter of 0.8 centimeters. So the diameter of this tube is 0.8 centimeter, and also it is thin walled. In other words, we don't have any conductive thermal resistance for the wall of the tube, and we can ignore the thermal resistance for that. And also the DI, or internal, and the external diameter of the tube also can be assumed to be equal. Then we are interested to find the length of the tube. Find the length of this tube according to the desired overall heat transfer coefficient, or U actually. So if the overall heat transfer coefficient of the heat exchanger is 550 watt per meter square degree Celsius, we should determine the length of this tube to achieve this overall heat transfer coefficient. So if we call this as L, we are interested to find this L for U equal to 550 watt per meter square degree Celsius. Okay, so how we can find this L? As you may notice, this L is effective on the total surface area of the heat exchanger, and the surface area is also effective on the overall heat transfer coefficient. So now let's see how we can find this L by our knowledge. Okay, let me just show you something at the end of the answer. As I mentioned in the question, also it was mentioned in the question actually, the tube is a thin wall tube, so the AI and AO, which are the surface area of the tube, the inner tube actually, will be equal to AS as a effective surface area for the heat transfer. And that effective surface area can be calculated by this equation. If you remember, this is the surface area of this tube, actually the inner tube. Pi, its diameter, it is given 0.8 centimeter, and times its length. So, but we don't have AS and we don't have L actually. So to find L, because it is our unknown, we can rearrangement this equation like this: L equal to AS divided by pi. So our problem now is changed to find this AS. AS is unknown. How we can find this AS? AS should be determined actually according to the overall heat transfer, or overall heat transfer coefficient, which is given. So now let's start the question from the beginning. The properties which we have are the specific heats of the two waters, the cold one and the hot one from the geometrical fluid, and they are given in the question. They are our nouns. First, let's calculate the rate of heat transfer for the cold and hot water. For the cold one, actually, we can use this equation to find its rate of heat transfer, Q dot equal to M dot Cp times T out minus T in for the water, which is our cold fluid in the heat exchanger. M dot as which is the mass flow rate of the water is given. The Cp also is now. T out and T in also is now. So just by substitution, the M dot is given for that is 0.2 kg per second. The Cp for that cold water, cold fluid is 4.18. And also the temperature for T out and T in, as you see in this figure. The temperature, the two temperature at input and output of the heat exchanger for the cold water is given. By substitution, we can find this Q dot for the or the rate of heat transfer for the cold fluid. So the cold fluid or the water will last this much of the thermal energy or heat. What about the hot water or geothermal water? We know its initial temperature and also its mass flow rate and specific heat. The rate of heat transfer for the geothermal water or the hot fluid also can be found by this equation, the general equation. Q dot equal to, again, M dot Cp T in T out for the geothermal water. Here we know the M dot for that water, we know Cp, and we know T in as well. What about T out? We don't know how much is T out, but we can assume that all of the heat which is lost by the cold or all of the heat actually received by the cold water, which has increased its temperature from 25 degrees Celsius to 60 degrees Celsius in the exchanger, comes from this geothermal water, and we don't have any thermal or heat loss in the heat exchanger. By this assumption, we can imagine that Q dot for the hot water for the geothermal water is equal to Q dot for the cold water. All of the heat or rate of heat transfer from the or to the cold water is equal to the rate of heat transfer from the geothermal water. So also we know the Q dot, which is 29.26. Then by rearrangement of these, we can find this equation, which is rearranged to find the T out or the temperature of the geothermal water at the output. Then by substitution of T in for that 140 degrees Celsius, the Q dot we have calculated in previous steps by knowing also the M dot for the geothermal water was 0.3 kg per second, and also the CP was given 4.31 kilojoule per kilogram degree Celsius. We can calculate the T out for the geothermal water. Now we have the four temperatures: the input and output temperature of cold water, and input and output temperature for the hot fluid or geothermal water. Okay, in next step we use the logarithmic mean temperature difference to find, actually we are going to use this method to find use this equation to find AS according to that, because in this equation Q that is already known, delta T Lm or the logarithmic mean temperature difference we can find here, because we have all of the information which is required, all for temperatures. Then the only unknown will be U, AS actually, and we can find it. U was also given in the question, if you remember. The only unknown is this one. Okay, so let's first use the logarithmic mean temperature difference. Delta T1, if you remember from previous slide, is equal to TH in minus TC in. Here TH in or hot fluid is 140 degrees Celsius and TC in is 25 degrees Celsius. So delta T1 will be 115 degrees Celsius. Delta T2 was TH out minus TC out. So TH out we have calculated 117.4 degrees Celsius minus TC out, which is 60 degrees Celsius. Then delta T2 will be 57.4 degrees Celsius. And then by using the equation for the logarithmic temperature difference, which was delta T1 minus delta T2 divided by ln, or Neperian logarithm of delta T1 divided by delta T2, we can find the delta T Lm or logarithmic mean temperature difference. Okay, now we have all of the information which is required to put in this equation. By rearrangement of this equation, we can find the AS or effective surface area for the heat transfer in this heat exchanger. We know Q dot 29.26 we have calculated here. We know U because it is given, or it is overall heat transfer coefficient, and delta T Lm we have calculated. Finally, the AS will be 0.642 meter square. Finally, as I said at the first step, we can use this equation to find the L, which is the equal to the effective surface area divided by pi d. D is the diameter of the inner tube. And finally, the L, or the length of the tube, will be 25.5 meter. Almost the line tube is required to reach this heat transfer and to reach this temperature for the water, the cold water actually. Okay, here we have another problem related to the heat exchanger, and we will see how we can use the LMTD method again. Okay, we have a double pipe counterflow heat exchanger which is going to cool ethylene glycol, which is specific. It is 2560 joule per kilogram degree Celsius, and it is flowing at a rate of 3.5 kg per second, and its initial temperature is 80 degrees Celsius. It's going to be 40 degrees Celsius when it goes out of the heat exchanger. And this cooling process is happening due to the heat transfer between the glycol and water, which is its specific heat is given, and its initial temperature is 20 degrees Celsius, and it leaves the heat exchanger at 55 degrees Celsius. So the cold fluid actually is water, and the hot fluid is ethylene glycol. The overall heat transfer coefficient based on the inner surface area, in other words UI, this UI is the overall heat transfer coefficient based on the inner surface area of the tube, and which is 250 degree watt per meter square degrees Celsius. So this is UI, we have UI. Then we should determine the rate of heat transfer, Q dot, the mass flow rate of water, M dot of water, and the heat transfer surface area on the inner side of the tube, AI. So the unknown are Q dot, M dot of the water, and also AI. And you can see here a schematic of the heat exchanger. The hot fluid is hot glycol. Its initial temperature and final temperature is given. It is decreased, and its flow rate also now. And the cold fluid is cold water, which is initial temperature 20 degrees Celsius, final is 55 degrees Celsius. And please notice that here we have a counterflow heat exchanger, or double pipe counterflow heat exchanger. Okay, first let's see how we can find this Q dot. As usual, we start with the properties. The specific water and ethylene glycol is given on the questions instruction. So the rate of heat transfer can be again calculated by the general equation. Q dot is equal to M dot Cp T in minus T out for glycol. Because for glycol we have M dot, we have Cp, we have T in, we have T out. Then we can find this Q dot. M dot for the glycol was 3.5. Cp was or is 2.56, and the initial and final temperature are 80 and 40. So this Q dot, or rate of heat transfer for ethylene glycol, is 358.4 kilowatts. And as I said for previous problem, here also the Q dot for ethylene glycol should be equal to Q dot for the water, or Q dot for the cold hot fluid should be equal to Q dot for the cold fluid. So the rate of heat transfer from water must be equal to the rate of heat transfer to the glycol. Now we are going to find in the B part of the question, find the m dot of water or mass flow rate of the water. So again we can write this equation, m q dot equal to m dot cp times T out minus T in for the water this time. Now q dot is known, we have calculated in previous step. M dot we don't know, cp is given in the question instruction, T out and T in also are the given parameter in this question. So only unknown is m dot. So by rearrangement of this equation we can find this m dot for the water or mass flow rate for the water is equal to rate of heat transfer divided by these terms. Then by substitution of the q dot we have calculated 358.4 divided by Cp for water. Here we should in this equation use Cp for water times the temperature difference for the water at the input and output of the heat exchanger, which is given 55 degrees Celsius minus 20 degrees Celsius. So the mass flow rate of the water is 2.45. After calculation of this, we will find this one as the mass flow rate for the water. Okay, now we have calculated A and B part. Actually, in the B part we was looking for this m dot. Now at the C part we are interested to find the AI or the surface area at the inner surface of the inside tube. So we can use this equation, this general equation, to find any of the parameter in the equation. Q dot is already known, we have calculated. UI was given, if you remember, in the question. This is UI, and AI is unknown. Delta Tm, which is the log mean temperature difference, is a parameter which we can calculate by this equation. This is the equation to calculate delta TLM, which is delta T1 minus delta T2 divided by Ln delta T1 divided by delta T2. Delta T1 and delta T2, according to the definition, are like this. Delta T1 is Th in minus Tc out. Th in means the temperature of the hot fluid at the input to the heat exchanger, which is ethylene glycol, and it is given 80 degrees Celsius, minus Tc out, or the temperature of the cold fluid at the output of the heat exchanger. So by substitution we can find the delta T1. Delta T2 is the Th out minus Tc in, temperature of the hot fluid at the output minus temperature for the cold fluid at the input. Then by substitution you can find the delta T2 as well. By substitution of this delta T1, delta T2 in the equation to find the mean temperature, log mean temperature difference, we can find the delta TLM, which is 22.4 degrees Celsius. And finally, as I said, we can just rearrange this equation to find AI or this heat transfer surface area for the inner surface of the tube is equal to Q dot divided by UI delta TLM. Q dot is now, we have calculated, UI is given in the question instruction, and delta TLM we have calculated here. By substitution and calculation, finally we get this 64 meter square for the AI as a heat transfer surface area for the inner surface of the inner tube actually. Here is another example for the heat exchanger, how to use that LMTD method to find different parameters for the heat exchanger. Okay, here glycerin and ethylene glycol actually are two fluids, and as you can see from the schematic figure for the question, is the double pipe. Okay, now let's see the detail of the question. Glycerin with this specific heat at temperature of 20 degrees Celsius and with 0.3 kilogram per second mass flow rate. So this is m dot for glycerin. Is to be heated, and this is TH or T. Okay, let's say it is TH or TC is to be heated. So this is TC in by ethylene glycol with this specific heat. So two fluid are glycerin and ethylene glycol, and glycerin is the cold fluid and ethylene glycol is hot fluid, which is the initial temperature for the ethylene glycol is 60 degrees Celsius. This is as shown here as well. This is TH in, and these two fluids are in thin wall double pipe. Thin wall means UI will be equal to UO equal to US, and AI will be equal to AO equal to AS. Thin wall means these terms actually. The temperature difference between the two fluids is 15 degrees Celsius at the outlet of heat exchanger. So this term means okay, this is the hot. This is hot fluid, hot ethylene glycol. So this is the TH out, TC out. So TH out minus TC out is 50 degrees Celsius. This is the other information which is given in the question. Then if the overall heat transfer coefficient is 240 watt per meter squared degrees Celsius, this is U, and UI, UO, and US, generally all of them will be equal to this. And the heat transfer surface area is 3.2. It is not mentioned inner or outer surface because it is thin wall, so this is A as well. Determine the rate of heat transfer, Q dot. Should determine the Q dot. And in the B part of the question, we should determine the outlet temperature of the glycerin TC out, and also we should determine the mass flow rate of the ethylene glycol, m dot of ethylene glycol. So we have three parts in this question, and we should find Q dot, TC out, and m dot of the ethylene glycol, which is the hot fluid, or m dot of the hot fluid. Okay, first let's find this Q dot. Okay, to find Q dot, we should use this equation for the heat exchangers. We should use this equation when we are going to use the LMTD method actually. So we can find Q dot by this equation. Q dot equal to U, it is given. AS is given as well. But what about delta T LM as the log mean temperature difference? Okay, so let's calculate that delta T Lm. Delta Tm is equal to delta T1 minus delta T2 divided by Ln delta T1 divided by delta T2. And as you know, delta T1 is the temperature difference at the input of the heat exchanger, and delta T2 is the temperature difference at the output of the heat exchanger. Here is parallel flow heat exchanger, so the delta T1 is temperature difference between these two temperature, which is 60 minus 20 degree Celsius, 60 minus 20 degrees Celsius, which is 40 degrees Celsius, delta T1, and delta T2, or temperature difference at the output of heat exchanger, is TH out minus TC out, or temperature difference before the two different fluid at the output, which is given TH out minus TC out is 15 degrees Celsius. So by substitution, we can find this delta TLM as a log mean temperature difference. Then by substitution of this delta Tm in the equation to calculate the rate of heat transfer by LMTD method, we can find the Q dot. So Q dot for this heat exchanger will be 19.58 kilowatts. For the B part, the outlet temperature of the glycerin is required. Again, the Q dot for the glycerin can be found by this equation. Q dot is equal to m dot Cp T out minus T in. M dot is mass flow rate of the glycerin, which is noun. Cp is the specific heat of the glycerin, which is noun. T out we don't know. T in is also known. And Q dot we have calculated for part A. And if you notice, this is this Q dot for the hot to fluid one, and for the from the hot to cold fluid, and is equal to the temperature which is received by cold fluid from the hot fluid. In other words, Q dot for hot and cold fluid is equal to the total, or the Q dot of the heat exchanger actually. So by rearrangement of this equation, we can find T out, or temperature of the glycerin as a cold fluid, which is 47.2 degrees Celsius. At the C part of the question, we should find the mass flow rate of the ethylene glycol. Again, we use this equation, Q dot equal to m dot Cp T in minus T out. Q dot is noun, m dot is unknown, Cp is given in the question, T in and T out for the ethylene glycol. The T in is known, as you can see here. T in for ethylene glycol is given, which is 60 degree Celsius, but we don't know how much is T out. How we can find that? It was mentioned in the question instruction that T H out minus TC out is 50 degrees Celsius. We have already calculated this temperature for the glycerin, which is the cold one. So TC out is 47.2. Then TH out will be plus 15. So this is the TH out or T-ethylene glycol out actually. Then we have also this. By substitution we can find this and that. Here they are changed. This is the T in, this is T out. It is written and vice versa. Only we are interested to know the value actually. Here ethylene glycol is losing heat or thermal energy, so its value is equal to the temperature which is received by glycerin, but with a different sign. What we are interested is its amount, and is 3 point, here is amount of the mass flow rate, which is 3.56 kg per second. If we put here 60 minus this value, this will be negative, which is not acceptable, so we only are interested about its absolute value of the rate of heat transfer. So the mass flow rate for the ethylene glycol or hot fluid is 3.56 kg per second.